Hello, everybody, and welcome to the third and final day of the Quantum Science Days of the Quantum World. Today we are having the first session almost fully, but not explicitly, dedicated to a secure communication. And we are very glad to invite our first speaker. It will be Elham Kashefi. And she is a professor in quantum computing. And not only, she is also a co-founder of a company that has been practically bringing into the world one of the first cloud computing services that was thanks to Elham going all the way from the theoretical to the implementation and commercialization chain. So we are happy to have Elham here with us, and the floor is yours, Elham.
Thank you very much, Oxana, for the kind introduction, and thanks everyone for the arrangement and for the invitation. I'm so glad to be here. So as already advertised, I'm going to tell you a little bit about the vision that we have. Is a bit combined with both the research I'm doing at Edinburgh and Paris as part of various consortium, as well as the company VeriCloud that I co-founded. And that's the vision that we believe quantum computing will become eventually like as a service. And in order to reach to this scalability of the service, we need to add several other aspects to the current cloud system that we have. And that's what I want to call towards the vision that you have secure and verifiable multi-tenant quantum data center. So most of my talk is to share the details, the vision and all the building blocks. Although Oxana kindly said that we have done it and we have brought it, but still there is many elements to be done. These are just building blocks of the Lego that we are going through it. So I can vision it, and hopefully there will be time to discussion to go through it. So let's just to see what the vision is. So right now already, if you look at what we call quantum network, these quantum link exist. I put some of them, there's plenty of them around the world. The Chinese link is one of the biggest, but these are QKD link, if you want. So they are essentially single node that are connected together. On the other hand, we also have quantum computer that in the future quantum internet, you can call them to be quantum node. And in some recent project that we have been part of it, Quantum Internet Alliance and EU project, we have saw the first step of really putting the network and the link and node together. So this is the picture from experiment by the TU Delft group that they show how all these various nodes, now they can be connected, and in the sum of the node, you have more capacity than just a single qubit receive and measure, which allow you to do more interesting protocol and application to be done. So essentially, if this is today, we can predict the future is going to be this beast. What I'm really thinking, we will eventually have data centers very similar to the current data center that we have. You have this virtual data center, you have this various hardware of the various type. They are connected using optical link, using fiber link, using quantum link. And if you look at it, the memory exactly like what we're doing. So there is all this green part, if you see in one side, that when you come and you're trying to run something on your cloud, there's all this distribution, all this stack layer, etc. goes through. But what is so different than the current existence, as I will talk about it, is that we are having these distributed things that is allow you to address scalability in the sense that how do I distribute tasks between various hardware that I have, but also the target is to not just mimic what exists classically data center. We want to increase the efficiency, we want to increase the security, and we want to also increase the integrity of our data. So that's the vision, that why the multi-distributed quantum data center might be even stronger than the counterpart. And just to make sure that we are all seeing where I'm heading, so I give this sort of use case example that I have, so that imagine that, want to look at this particular privacy preserving quantum machine learning. So it's very likely, if you look at the same thing in the classical, you will have a party which have their data. This could be a bank who wants to do synthetic data and they have a private data that they don't want to share with the others. Then you have another party, another organization, some some software company who have come up with the best algorithm that they are allowing to do some sort of classification and synthetic data production. but they have their own algorithm, and very likely somebody else has built the hardware and there is a quantum services doing it. So we need to ensure the privacy of data, integrity of the computation in this distributed infrastructure is done. And that's the target that I want to show you, that where we are in reaching to this dream that everybody come and they connect and they are provided all the services that we want beyond the current status of art. So what is the state of art right now? So we start the question by saying, let's assume we have just two parties. This is the classic client server model, that they have an honest client who wants to come to be plugged and run some quantum computation in a remote server, but this server could be malicious. It might be, you don't want to give the data, as I'll describe it, etc. So this is the first step of our building block. And what we know is that the first result that I want to present is that over the years, we have proved that quantum communication is necessary. And that's quite interesting for all the talk that you have seen. This is to some extent is the necessity of quantum communication for achieving such security, as that's what I would call a quantum communication advantage, if you like. And the building block of it is the thing that we have had, like a quantum key distribution, teleportation, self-testing, and that gives us this very old result that we have had, is verifiable universal blind quantum computing. So in this scenario, I will reach to show you exactly where we are, how many protocols have been designed, how we have optimized it, where we are, and how far we are to make this one a reality of implementation. But then we want to go further away, and then you see that, okay, if I have the honest client malicious server, it's very likely that you need to go to the next, and your client could be malicious. Maybe the server which is providing your data, they also want to have some protection, somebody's not hacking their system, whereas the client, might just essentially is not interested to running the data, trying to hack the system, or even apply and use the service and then later on claim that nothing has been done. So in the crypto world that we are living, everything needs to become more obnoxious. So now the client could be malicious, and then again I describe what's the state of art. How does this become a little bit like a computation world, that we bring in classical and quantum things together? So we're using some classical primitive to allow us to deal with this malicious client as well as everything. But because our requirement is higher, because now we want to do something that even the client is malicious, you will see that suddenly the building blocks are a bit bigger. It's not only enough to have the QKD teleportation self-testing. On the client, we need to have memory, and the things becoming a little bit more challenging in technology-wise, and the technique that I will present. And finally, really what I was presenting, this multi-tenant, etc., that's toward the multi-party. And there you have several clients. Somebody has the data, somebody has the algorithm, somebody have infrastructure, or you want to have shared data because they want to look at, I don't know, Amazon and Google want to collectively calculate some intersection. So in this scenario, again, we need to look at what existing classically, and the general result that I will show you is that how we take the classical secure multi-party computing and we lift it to the quantum. And again, what is the challenges? And if I get the chance, depending on our minutes, is that then I would be able to come back to our thinking in the very cloud as our startup is like, we have building the architecture to allow us to get these things closer to the reality, to be able to build on top of the QKD network, all the way to go to deliver this secure, quantum secure multi-party computing. So that's sort of state of art, and also the plan of the talk. So I start to giving you a building block of the first one, and the thinking that I hope you will able to see, that everything is very modular. Of course, this is the result of like my last 10 or 20 years of research with so many colleagues and collaborators, but the thinking is really building block, that is not like every time I go from 2-party to 3-party, I need to completely reinvent the wheel. Or if I want to make my honest client, malicious client, is a completely new protocol. We really feel that now there is a sort of a new methodology to think that, and every time you just add a little bit, which is more similar to the thinking that exists in classical. We have this composable scenario to build on top of it. Okay, so let's go through this. And so the very first step, back to the current, what I call insecure quantum cloud services. If you look at it, all the services that we have, the model behind them are has been always educational model or kind of exploration model. So everybody is very happy to write their whatever quantum circuit algorithm that you have in mind, you're running it, and then you go to the Amazon bracket and etc. And you use the classical internet to communicate from your local laptop to run something on the quantum computer, which is impressive. It's amazing that we can already do that, but it's insecure in the following way that there's no privacy. When you write a little algorithm, your data, your algorithm, your result is completely public, or even if you wish, is completely known to the hardware provider. And on top of that, the other challenge that we have all of these things, there's also no verification, especially with these sort of devices that they have. They are NISKI. You don't know if there's really quantum computer is there plugged. You don't know if these devices are so noisy. You don't know if the results are correct or not, because we cannot even classically simulate. So for us, a decade ago, when we started looking at these challenges, that how could we provide both the privacy of our data as well as the integrity of data. So that's the setup, the problem that started. And then what we realized, and what is the message before I go ahead and fast forward, is that you need quantum internet, you need quantum communication. So essentially, if you want to address the question of verifiability and privacy of your data, quantum communication is necessary. So this is an old paper we write with Scott Aronson and two of my students, Alexandru and Alexandru, the both amazing Romanian students who are now building the entire infrastructure under this thing. But it was very surprising result to show that if we want to have information security in this sort of delegated computing, that I run my computation, my algorithm, my data remain completely secure while I'm running it on the quantum server, the quantum communication is required unless polynomial hierarchy collapse in the third level. A little bit like, this sort of supremacy result that you're hearing, boson sampling cannot be classically simulated, etc. It's the same sort of very different type of proof technique. And I have to be a bit honest, when you open the paper, it's not as strong as you want because it's relative to an oracle. So there's some sort of complication, but you can consider this result as a first indication that why doing this desire secure, privately verification in an information secure cannot be achieved using classical communication. There is an entire other area of research that maybe I get a chance to talk or not. If you're happy to settle for computational security or something that is called post-quantum security, using some sort of other primitive and assumption that some problem is hard even for quantum computer, then we can do it with classical, but there is an overhead comes to it. But currently our thinking is that you have to have quantum communication between your client server to achieve information security. So in a sense, for the rest of our talk, I take this on as an axiom of cloud, if you like, that it's the practical, secure access to quantum cloud requires quantum communication. Now that we established these things, so we want to build it and we want to find still minimum. So the thinking is very important. We want to have a solution that is scalable. So we want to answer the question, what is the minimum amount of quantum communication and quantum capacity I need to give to a user to run something on a quantum computer? If the answer is that you need to buy a quantum computer for yourself, well, it's nothing to do with the cloud services. So we go to this sort of asymmetry. What's the minimum a client should do to be able to achieve the property? And that was this old result with my colleague Anne Brodman from Ottawa and Joe Fitzsimon from Singapore, who also ended up to set up a company, Horizon, as well. So the picture, I don't go through the details. I'm hoping that people have heard about this universal quantum computing. I want to build more on about it, but the building block of it is interesting. The building block that allow you to do this is QKD for encoding, teleportation for computing, and a trap for testing. So think with me, I don't want to give the mathematics of thing, I want to give you building blocks. So in this picture of this protocol that you see, all that the client is required to do to prepare single qubit, and they could be in one of these sort of QKD type of a state. They could be 0, 1, or plus theta or minus theta, where theta is some sort of 8 random state in the XY plane. And as soon as this device, this single photon source, or this random single qubit, if you want this prepared, they are sent to the server, who's supposed to have the capacity to entangle them, to run the computation on them, to keep them coherent, and etc. Part of it But that's what I mean. So on the client, you only need the preparation of QKD state. On the server side, instead of just receiving and measuring, you need to do quantum computation. And there is this terminology that comes later on that some of those qubits, the red qubit, are the computation qubit. Some of those qubit is called dummy qubit, and you will see why they are there, because they are creating some sort of disentangle between region. And the orange qubit are called trap qubit for testing. So this allows us to achieve exactly the protocol that is there. And if you like, you can look at the details later, is that by a very simple interactive structure, I just create lots of qubit. Think of this qubit like the key for encryption, you know, and then you run your computation remotely on a quantum server, and you're able to hide what your computation is, because the server does not know which is the red qubit, which is the dummy qubit, which is the trap qubit. They are achieved as a general quantum state, and hence, thanks to uncertainty principle, you cannot exactly know this qubit. And at the end of the day, you can also even test whether the computation is done correctly or not. I would love to spend some time to tell you this thing, but then I would not be able to tell you nothing. And usually I just end up to talk 1 hour from ubiquity rather than a thing. But let's assume, unless you complain, and I see there is some question in the chat, so you can interrupt me if somebody read those questions for me, that you understand that it is possible to achieve universal secure quantum computing, that the privacy of the data and algorithms achieve, but on the client side, you only need to have this QKD part, and on the server side, you need to have the teleportation and the testing. And then the rest of the story is that, okay, what do I need to add to this thing to achieve what I advertised at the beginning, that I might have multi-server and I have multi-client, and they might be actually malicious, because here the client is following the instruction. Okay, I see there is a lot of questions, so maybe I cannot read the chat because I'm in the full screen. If somebody...
Don't worry, Elham, I will read them for you if you prefer right away. Otherwise, we can also keep them for the end. But as you asked, I assume you prefer. So
yes, maybe we can answer. Yes, please.
The question was, does the verification of the quantum machine requires also quantum communication? So you were saying one is a security, another is the verification. And it's a question from me. Actually, I'm curious whether verification also requires secure channel.
It is correct. So there's so again, if you want to do a verification with making no assumption whatsoever on your device, no assumption regarding the noise, no assumption regarding the device is quantum or not, no assumption regarding like based on some sort of a post quantum security thing, then you need quantum communication. And in fact, this is still an open question. So you're right. You know, if I quickly go in here, I cannot go to my thing. So okay, it's going just for, yeah, no, it's come here. So what I showed in this, sorry, in this slide, in the work that we did, oh, my apology. This work, we showed that if you wanted to have security of the computation, you need the quantum communication. So you can completely correctly answer the question, okay, let's say that I don't care about hiding my computation, I just want to have verifiability. We have not shown that it's impossible to do verification of quantum computing with classical communication. Is not known to be unknown. There is a very important result in the field that came a few years ago by Mahadev that some of you might have seen, that is show that actually you can classically verify a quantum computation, but there is an assumption there. You're assuming that you're using LWE, which is a problem that is believed to be even hard even if you have quantum computer. So if you're happy to assume this sort of, there is something that cannot be done quantumly, then our no-go result disappear, because it's no longer information secure verifiability, or not, it's no longer information secure private computation, is computationally secure. Then you can use all of this gadget of the classical part of it. So it's a little bit of the state of the art. I would say that I don't have a proof, but I strongly believe if you want to have this very, very solid type of verification that you don't put any assumption, I doubt that you can do it without quantum communication, but that's a still open question. Thanks for the question.
Okay, many thanks. Actually, there is a quick other question that I invited Zeki to ask himself, as we have started this kind of intervention during the talk, which I like a lot. In some countries, this is the standard. In Europe, it's less a standard, but I'm glad that we are combining standards. So Zeki, please unmute yourself and ask your question.
Thanks, Oxana. So my question is, did you encounter or run any studies on the requirements of special purpose blind quantum computing rather than universal? And are there any serious resource requirement differences between those two models? Because I think this model is really resource intensive, and we are still probably at least one or a couple of decades before this can be implemented.
Exactly. So this is a fantastic question leading to the rest of my talk. So because if you saw that paper that we wrote, it was 2009. And as you can see that, like, why not everybody is implementing this thing? Because in fact, what we show is very practical for client. I would say, well, the client just needs to have single qubit, there is no quantum memory, etc. But what I show you, as Zaki is asking, is a nightmare for the server. For each computation, you need to create this giant cluster state and etc. And on top of that, back to the special purpose devices that you were mentioning, they are also oversensitive and they have a huge overhead. So indeed, being able to go all the way to make this thing for a specific devices, for a specific computation and bringing the overhead, this thing is something that we did in a very recent work that, I'm happy to briefly mention that. To me, it was kind of like completely changing the way, we call it securing quantum computation in the NISQ area, in the model that, we will understand that our devices are not perfect. They're not fault-tolerant logical qubit. They are physical qubit, as well as also reducing the overhead. So this one, I go a little bit through the details of it to show you. And it, to some extent, should answer your question that what if I just want to, like, for example, secure my VQE type of algorithm? I don't want to have universal gate. I just want to do part of it. So these are exactly this new framework that we have developed that is allowing us to move for the specific particular computation. So I see there's a bunch of more questions. So in order, before completely convince you that we have the solution for this special case, maybe I take other question that is relevant to this part, and then I continue with showing that how we have improved the overhead and making them much more practical. There must be 4 more questions or 3 more questions if I just is this thing. Sorry.
Elham, in fact, sometimes in the chat there is also exchange. So, for example, somebody entered and say, "Hi, I just entered from this and that."
Okay, good.
So
good.
please
okay, so.
don't worry. Whenever there will be a question, I will address it to you.
Okay, so I see that this is a blind chat, so I was a very secure chat. I cannot see the content of it. Okay, so I continue. feel free to decide whether the question can be done later on or during the talk, but I'm very happy to answer. So exactly as motivated by a part of it, say that, like, the current protocol that has been developed, and there is millions of them, there is a lot of protocol on this part, there were shortcomings in several ways. And these shortcomings are very important, again, because we want to build the infrastructure for the multi-party, etc., etc., etc. So there were, what was the shortcoming? The shortcoming was that they were oversensitive. So it means that if your server was, it was not a malicious server, it was a really quantum computer, but it was a little bit noisy, we would reject all the computation, we abort. So essentially, and in fact, we were running such computation on the Rigetti device, and they really have a quantum device and it's impressive, but we would always reject because it was oversensitive to noise. So we address that question by showing that there is a way to exponentially boost the verification to be very, very still robust, and yet allowing a level of the noise as long as we call it honest but noisy device. So in a sense that if we know the threshold of our device is 90% fidelity, and we are happy to accept our computation within that fidelity, we integrate that in our protocol. It's no longer, unless you give me perfect device, I'm not going to accept your computation and everything collapse. And the other most important part that some of you who already captured that this is a huge intensive is that, in a sense, we create no overhead. Let me explain to you why we really think that is no overhead. So imagine this is your target computation. This is your algorithm that you want to run, for example, on psi-quantum, because it's a cluster state photonic quantum computation. They're creating this sort of entangled resource. You know, you can say that I want to have this graph state of the 5-qubit. Each of the qubit you prepare in plus, and then you're measuring each one of them a particular way. That's your target computation you want to do. And now you want to say, okay, I want to add a privacy and verification on top of it. How much extra overhead I need to put at it? And the answer is none, in the following way, that all you need to do, instead of directly give the alpha 1, alpha 2, alpha 3, alpha 4, alpha 5 to psi-quantum to run your computation, what you do, first send individual single qubits. So if your computation is 5-qubit, you only need to send 5-qubit, not 6-qubit, 5-qubit. So you send the 5-qubit that they are previously randomized with the theta I rotation. And then instead of telling alpha 1 to the server to run the computation, you give alpha 1 prime, which is compensating for this theta 1 and some sort of feed forward. So that's the first part of making it a blind computation. And it's strange because, of course, this has been always the case in the previous protocol, but we were not able to show that this is enough in order to achieve verifiability and composability, etc. We always had extra things as part of it. So if you're happy to be limited to a specific resources that you have, and you're happy to give that information to the server that, look, I'm doing a computation of 5-qubit, but you never know which 5-qubit computation I'm doing it, because you don't know, am I implementing Grover or Shor, or am I implementing a VQE or whatever computation that's fit inside this thing, that's all you need to do. So essentially, you have your target computation, which is what we demonstrate with this gray, and the same infrastructure, the same resource, the same kind of entanglement, the same set of gates without changing your device is also used in a different round to be the test. So this coloring of the graph is showing that you can choose any qubit to become a trap qubit, and all the other colorful orange, green, blue, if you're seeing it's called dummy qubit. And then the computation is a computation that I have no clue what should be the result. They are probabilistic or whatever computation I'm running it, and it could be beyond the capacity of classical simulated. But we're creating a trap. If you see all those edges, although they seems to be entangling, but they are, because of the qubit being dummy, is not entangled, and they give me deterministic computation. So the computation pictures become like that. So what we call test and compute model. So you want to run a 5-qubit computation. And what we say is that if you want to add the privacy and test, always stick to same 5-qubit computation, but run it 100 times. And that's a huge difference in terms of overhead, in the sense that before we would create a 100-qubit computation in order to get out of it a 5-qubit correct computation. But we just discovered that there is a need to be the case, or actually I should claim that my student discovered that I was wrong to define the paper originally like that. They have shown that it's enough to do the repetition. And repetition is okay with our quantum computer, because you said that today I'm going to run a gray computation, tomorrow I'm going to run a computation which is test, another half an hour later I'm doing it. The server does not know, are you in a round which is a test round or in a computer round? You run all of this thing, and then you look at the overall threshold, in a sense that I, as a client, have sent those single qubit, if you remember. I know when is the deterministic computation and what should be the result, and I know which one is actually computation. And now I look at all the result of my colorful test, and if they pass and they are exactly my expected outcome, we proved that it gives you a high fidelity in terms of making sure the rest of computation is done. So this is the part that I'm super excited. I think is very, very unique to the quantum communication that allow you this thing. By doing quantum communication, we are obfuscating from server's point of view when I'm testing him, when I'm computing. And this goes to another whole theory of the proof that essentially you're truling the noise. So whether the noise is a malicious noise or is actually device noise, it cannot be indistinguishable, and is enough to do, if you like, tomography of your noise on your test run to give a confidence about the computation on your computer run. And that's the only way we can deal with the exponential space of the noise. So now, if you see in my reasoning, although I didn't show you theorem, but I'm making no assumption about my noise being Markovian, non-Markovian. I didn't assume that whether the device is quantum or classical. I didn't no assumption about whether there exists some problem that it seems to be hard for quantum. I just say, that's it. I'm sending quantum communication. Using that, I create this sort of test versus computation, and we prove in a compositional way that if the majority of the outcome of computation of the test run are correct, by doing error repetition that we have done, we get the majority of the great computation, and we have boosted also the noise. So if some of my great computation are noisy, because I'm taking also the majority vote of outcome, my computation is correct. So that's the thing that we call it a practical, efficient solution in theory for verifiable blind quantum computing is done. And this is a very recent result that we have part of it. So, and if you look at it a little bit backward, this result already in the photonic are very natural to be implemented. We had this old result by a group of Philip Walter that you can call Alice to be the client, the server. Okay, they were just really close to each other. They are not on the cloud. And it's because everything is photonic, it's very easy. You have the photon for communication, you have photon for computation. Then there was another experiment by the John Pan's group that they show it in a much, much larger distance part of it. And there's several other experiments that as long as we do photonic, this can be done. But what about the other? Because this question has been asked that, okay, let's assume that my claim that for the photonic quantum computation, we can demonstrate them, although even in photonic quantum computation, there are some, like for example, Xanadu is one of amazing platform. We have been talking to them, but the fact that we need to have adaptivity and send the photon from outside to inside is create a noise. So we need to be a little bit more patient so the quality of all these NISQI devices become better. But I believe for photonic quantum computation, we should be seeing some sort of a scalable demonstration soon, and at least that's the target we have for VeriCloud. But for the other platform as well, like other matter qubit, like an ion qubit, like a NV platform, etc., this become also a little bit of that. There is no-go result. It's just a matter of how do you do photon matter transduction. So if there is a way that you can transfer the single qubit rotation that is come as a QKD platform from client to become transformed to a randomization under your matter qubit, then you are in business. And we're trying to do some proof of concept, such implementation with the NKIT platform of the ion trap in UK, as well as with the NV platform in the TU Delft. So we have those conversations. You're right, the question that was asked before. We don't have them right now, but I'm optimistic that the building blocks are there. But can we scale it up? Can you suddenly turn the Google, or not the Google, the IBM cloud services to reach to here? We still have some way to go. We still need to optimize. So that was a long answer to the question that was asked. But in a sense, that closed my first part, that if you were talking about the honest client who want to really run the computation and make sure that the computation is done correctly, the data has not been leaked, etc. The building, but at least my job in theory is done. And now we really to completely keep continue and try to optimize. There is lots of optimization that can happen. That's why eventually at some point it's no longer theory. You need to have a startup, which is like go through the whole development of a full stack. Like, how do I optimize? Do I really need to send every qubit to be randomized, or can I send few of them? And these are all the type of questions that, in your stack software, you can address it depending on what aspect of your computation you want to hide, depending on how much trust of the certification you want to have. There is room to optimization. But the framework, I would believe that is like we are there. Of course, we can even optimize it even further. So that was the first part of it. I see that I need to make a bit of a faster move. We have another, if I'm correct, we have another 10 minutes, 20 minutes, 10 minutes?
We have 15 minutes, including questions.
Okay, 15 minutes to include the question. So I tried to a little bit fast forward, just to say that, like, to give you a feeling that why, when you build this first structure, everything else can come on top of it. So the next step is a malicious client. As I said, the question is like a payment denial, hardware hacking, identification challenge. So far we always assume server is nasty and we want to protect, but now we want to also protect ourselves against a potential client who doesn't want to pay the services later on, or even a scenario that maybe I have an algorithm and data, but I want to share part of this with the other algorithm and data that somebody else has. All of this platform exists classically, and you want to do it quantumly. And the beauty of it is that it still is the same thing, still is the client that sends the QKD. And if you look at it, I'm just adding a new line to it. I still do the same universal blind computation, QKD, teleportation trap. But because I need to check whether the client is acting correctly or not, I'm just bringing the commitment scheme into the picture. So here's, instead of saying that every single qubit that the client is sends to me, I'm immediately plugging to the server to run the computation. We need to check that whether the client is really malicious, in the sense that maybe sending entangled state. Maybe it's trying to pretend, oh yeah, I'm sending you a QKD state, but in fact, like the typical attack that we know about exists in quantum cryptography. I send a bell pair, I send part of a bell pair, and in order to later on to hack your system or get something out of it. And with this sort of entanglement attacking, you can grab a lot of things. So what we do, we call this qubit test. So the qubit comes, they need to be stuck first in the middle to run some qubit test protocol. And if the qubit test protocol pass, then we know that the client is honest, and then we plug it to the server. And the server still will be tested by using the previous mechanism. So that's the module Lego. We take our UBQC, we plug it in the middle, and this plugging in the middle is a commitment scheme. And the test is a very simple idea of the cut and choose that exists classically. So we're reinventing it in the quantum, in the sense that you send all of those qubits that you pretend and you're claiming that they are single qubit plus theta. But you need to also use a classical scheme to commit those value of the theta. So now, when I receive all of your qubit, before I run the computation, I ask you, okay, I'm going to use the qubit. Now, this time the server is testing the client. So the server said that, okay, client, please open the commitment, the classical commitment to the angle of the qubit 5 that you send me. And you claim this qubit to be plus theta. So give me the theta and make a measurement. I should get a deterministic outcome. So now we again proving, if you take few of these things and do the test on them, that give you a guarantee regarding the remaining, but only at then level, then you start going to the part of it. So in fact, this is a way that we are able to boost security from semi-malicious client to the fully malicious client. And it's very, very unique. I love to keep coming back to that. Is again, you can only do this sort of trick if the communication from client to the server was a single qubit communication. It's a sort of the magic of the QKD. We do not need to have more complicated state, and we can do this sort of cut and choose, as we have proven this paper, is that if in the qubit that the client, you want to check the client part, is only single qubit. So if you suddenly make the client to be too sophisticated, then we are back in the game, okay, everybody need to be running a sophisticated procedure. No, we just send the same single qubit, we do this sort of very simple test, and we go about it. So that's the structure, but of course it's very challenging in the sense that you need to have memory now. In the previous case, as soon as this qubit are come, you would have plugged to the server, you run the computation, but now the server need to create a gadget in the sense that qubit comes, I do some tests, and then I do the computation. So this one has not implemented, but I used to look at this is a very old paper for boson sampling in the John Pan's group, that they did something that is almost the infrastructure that we need, that the photon comes and they become randomized in these red things, which I don't understand very well. But what I understand is that you sometimes can take part of those things and do some sort of a test, in the sense that you can take some of your photon, and while the rest of photon goes in this delay, you can do some sort of little test on it. So these are almost like the idea of how using the delay, you can implement the same effect of memory test. But before you ask that question, I answer that, of course, this is a heavy demand. A lot of photon will get lost. There is an effect of infidelity, but it is what it is. If you want to take care of the client maliciousness, then you need to have a better memory on the server side to be able to run the test part of it. And finally, before we wrap it up, so finally, okay, now that I take care of the two-party, can we put all the bits and pieces together and really go for the multi-client, multi-quantum internet, running something distributed in a quantum computer? And that's some work we did a few years back with Anna Papa, which is now running her own team in Germany. And we look at the same thing, okay, surely we can combine this thing in the sense that now several client comes, each one of them has a random qubit. And then if I show you in this other slide, actually is better, sorry. So the protocol looks like this. So again, I'm having the same element that each of the client is coming. Each client sends their own random qubit, but now you want to have a collective randomness. And that's now the station we add in the middle is called qubit mixing, in the sense that before all the qubit from different client comes and plugged to the server, because nobody trusts anybody, you need to have this qubit mixing. So we have the QKD as before, we have teleportation for computation, we have a trap to test the server is not malicious, but we use beautifully the classical SMPC in order to be able to implement a qubit mixing. And this in fact came from an idea of the work. I need to give the full credit to everybody who comes from this work. So there is a very nice paper recently comes from the Amsterdam group that they somehow put this methodology that if the client want to put inserting a trap on the server, but nobody trusting each other, you need to make sure that everybody also testing each other. So the very first paper that used the classical SMPC to be lifted to go to quantum SMPC was this work. I don't think Stacey was talking about this in her talk, but this is one of the very nice work. And we used, inspired by their work, we also use the same thing in order to show that we can continue our multi-client ubiquity by also bringing SMPC. So that's the structure of the qubit. I don't know how clear it was, but the claim is that our protocol is very efficient as compared to everything, etc. You can look at the paper, but maybe the most important thing is that, back to my Lego pieces thinking. So if you really want to build efficient, malicious client, malicious server, there's a lot of module. What I like it is that there is a module which is a classical SMPC, and you might improve it instead of picking up a general one, because it's a very particular SMPC that you're using for collectively computing the measurement angle. And because it's a very specific function, maybe you can do it better. Then there is this remote state preparation, which is a hardware dependent, and I'm going to talk about it a little bit to see how we can improve it. And then there's a blind QC, but maybe we don't need to hide all the qubit. And there is a verifiability, maybe we don't need a dummy. So this is sort of a roadmap that we in our group is all trying to see that, okay, now that we have modularized everything, can we further optimizing it? The first optimization that we did to claim that this is good is that we look at this sort of qubit mixing. Currently, the qubit mixing is this animation is not correct, but currently the target of qubit mixing is that every client send their own QKD type of state, and out of it you need to create a collective state that, if you see this summation that I'm putting it, is taking a masking of a summation of all the theta. And the way you're implementing it is in this circuit that is under my text, my apology, but you see, like, you take the first, so the server receive a qubit that he doesn't know what it is, but he's keep teleporting it over top of the other qubit, that eventually the final qubit that he has, it has a mask of theta, which is the summation of all the masks that everybody has done. And this thing is implemented blindly, this is very good, etc. But it's heavy, because again, back to the kind of the memory delay that the server need to go. So for every client, each one of them send their qubit, the qubit goes to the server trying to mix them, trying to entangle them. Every step there is a loss, every step there is a loss. And then those qubits eventually plug to go blind QC. So we would like to make this one a bit more optimized. And that's what we did in some follow-up work that we did with the colleague from Edinburgh, as well as VeriCloud, that we realized you don't really need to make each client to prepare a quantum state and rotating it, and then send it to the server to mix it. So what we call it the rotating client, probably in this picture is better. So this is, now I'm stepping out and telling you a little bit about VeriCloud and the industry vision that we have. So VeriCloud has developed a new architecture that is called Q-Line. And the idea is that as long as we don't measure the photon, we can go from one client to another client and everybody's rotating it. And then when you do it in this way, already the qubit that arrive in the quantum computer is a joint mixing. They are very simple story that you would think that I should have seen it already when I was designing the first one, but of course it's a Lego pieces. So there is no need that each qubit from each client come to the server and server mix them. With the Q-line architecture, upon on their way, when they go there, each one is mixing. And this allows a much more direct plugging. So if you look at this picture that I was showing before, sorry about this. So before I was saying each client need to send a lot of qubit and is mixed the qubit mixer on the server side, but with the Q-line architecture, when it goes around, so if you think of it as some sort of like a ringed structure of the internet, everybody have a chance to put the randomization on top of it. And then we have shown that the whole SMPC goes through, but interesting enough, we don't know if this is enough for verification. So right now, the very open question is that we knew how with this more costly sort of star architecture to do verifiable, secure multi-party computation. And I finished my talk by saying that like, we are now working to see that this thing is enough for the privacy because the masking is enough, but we still have not completely figured out. And it's a very interesting, a completely foundational type of argument, another talk to tell you that why suddenly the fact that nobody has a trusted resource or trusted measurement, the problem is much more complicated to do verification. So for having privacy, only trusted rotation is enough, but for verification, you need quantum communication, maybe with the trusted measure, maybe yes, maybe no, but essentially that's where we are. I'm going to stop it, but this is the utopia that we believe, that we can put all these different quantum computing, especially the photonic one or maybe non-photonic one, we connect them with the Q-line architecture that we had, and we can run some sort of secure quantum data center. I hope it's going to be not in a too far distant research, distant future, but there is a lot of research questions to be answered. It's still not something that we can deliver. So it's a much smaller scale that we can show. I think I stop it here. Thank you very much for listening. And now I'm happy to answer any question that you might have. Maybe I stop my screen as well to see you.
Many thanks, Elham. This was an extremely enlightening talk and very introductive for people who are not from the area, as me, for example. And I'm glad to start. We have a couple of minutes for the questions. And I don't know if Syed Sharim would like to open the microphone and speak out his questions, or he would prefer me to read them. In the meantime, Mark Scrotson writes that it was a very impressive work, and thank you a lot for the presentation, as well as Handy. We have a lot of great feedback for you.
Thank you very much.
Okay, so I'm prompt to read. Okay, so first it said that the quantum computers and the network of multi-quantum system can run using quantum algorithms. But how do the classical to quantum systems be implemented using the quantum algorithms?
Okay, I'm trying to understand what you're trying to ask. So essentially, you're saying that quantum can be network of multi-quantum system can run using quantum algorithm, but how do we classical to quantum system to implement using the quantum? I really don't understand your question, but like, let me assume your question is that, okay, I have a classical algorithm and I want to run this classical algorithm on quantum computer. So the first question is that you want to see what advantage you have. So it's like the advantage in terms of the monolog quantum advantage is the speed. But what I'm presenting is that now you also achieve security and verifiability. Is that your question? How no cloning theorem and no broadcasting theorem can be maintained in this system, as classical systems have many similar copies, but in quantum computation cannot be implemented. Okay, so I think I'm getting where you're coming. I'm assuming you're coming a little bit more from the classical background. So the point is, that anything that we can do in classically, we can easily write them in quantumly, and the way to think of it, you just do it in the computational basis. So you can think that the classical computer is essentially a quantum computer, is work on the classical computational basis, and then you don't deal with the no cloning theorem of broadcasting, because as long as you work only with the computational basis, they are essentially classical and you can do everything. So this is for you the uplifting it, I just, rewrite them in quantum, but you shouldn't, because there is no point of doing it if there is no advantage. So that's one way to think. The advantage of quantum computing for solving classical problem or other quantum problem is that when we step out of computational basis and we start doing entangled state and non-decomposable, and indeed then the no cloning theorem or broadcasting theorem become part of it.
Okay, many thanks. This was a very deep answer. I think there was one more question in the middle, if I am not mistaken. Let me recover it. Oh, I do not see more questions. Okay, so actually it was from me again regarding the repetition instead of growing qubits. This was a very impressive result. And then as I was working all my time on the quantum memories and coherence, and I know that devices have this technical problem at the moment. So this then goes into the problem of coherence of the devices. So how long can you do the repetitions so that you can keep and compare the results from all of them? Am I right, or is it not the problem?
So let me clarify. It's a very good question. So because I went quickly. So first of all, this trick that we showed, that instead of growing the whole thing and keep everything entangled, we can make them, repeating the same computation, works only for classical input, classical output. So the story goes like this. So I have a 5-qubit computation. I'm running this 5-qubit computation and I measure, and there's nothing left to be coherent, and I write my classical outcome with me. Then I take the same computation, I'm running it again, and then I'm writing it. This is what's called the classical repetition code in a sense. So if the computation you're doing on a quantum computer is only classical input, classical output type of thing, like for example, you're trying to factor a problem, or you want to trying to find the solution of thing, not a quantum state, then the scheme is saying, okay, run them as quick as possible, run the computation, collect all the classical outcome, and there's nothing remain coherent. And then afterward, you do the analysis in the sense that those run that you call a test, you see if they give you the expected outcome. Those run that you don't have any idea there should be computation, you get the majority vote on that thing, and that become the computation. And that was surprising, because exactly as you said, because of the whole coherence attack in crypto, we were thinking that we always need to have the entire thing coherently remain to be the test. But if it's only dealing with classical output for BQP computation, repetition code, the classical repetition code is enough. And we have no idea if this can be also pushed for quantum outcome. Without it, and is much more outcome. But for the majority of algorithm we want to run on such something, you only want the classical outcome, yes or no, yes, this is the answer. So it's somehow that's where we're keeping everything coherence for the whole 1000 qubit that you might need. I'm breaking it to the 100 round of 100 qubit computation.
This is a scary door opener for all finals. All right, many thanks, Elham. This was a great start of our session, and I would like you to greet and say goodbye to the speakers in your mother tongue, because we have so many countries participating. I don't know, I think it would be very nice to hear it in your original language.
خیلی ممنون، متشکرم از اینکه به سخنرانی من گوش کردین. به امید دیدار. ممنون، متشکرم.
Many thanks.